Yep. So while you're considering these network theorems, they're going to be fundamental theorems that will allow you to analyze complex circuits. Yeah. Like I've mentioned earlier, we're going to consider four network theorems. Yeah. So today we're going to consider the again I mentioned the name superposition theorem. So in a few minutes we'll look at what is a superposition theorem and then the Thevenin theorem. Yeah. So we've considered the Kirchhoff's laws already. So we've seen the Kirchhoff's laws, the Kirchhoff's current law, and Kirchhoff's voltage law are fundamental laws which allow us to solve circuits using mesh analysis, loops, and so on. So this is fine. But the theorems you're about to study now empower you further to do very quick analysis for especially more advanced circuits. Let's look at the first one. So the name itself is saying superposition theorem. Now, what the name superposition is simply refers to the fact that if you have any circuit where you have more than one voltage source or current source, in a few minutes we'll explain what's the current source or voltage source, then the superposition tells you that you can study a circuit individually for each source, and then you do an algebraic sum of the responses you're getting for each individual source. It would be the resulting source. Let's say you have a circuit with, let's say, three sources, three voltage source. It can be quite difficult to analyze this type of circuit to get the overall response. If you have a given resistor, for example, and all the three sources will be supplying current and creating a potential difference across that load. So if your objective is to find the current or the voltage drop across that resistor, so one approach with the superposition theorem advocates is you can actually consider one source at a time. And then you take, for example, if you take source number one, you're going to get a current, let's say. You take source number two, you get the second current. Source number three, you get this third current. If you take the algebraic sum of these three currents, then you get the overall current you would get with the three sources. So as you can see, the superposition theorem allows you to simplify circuit analysis. Yeah. So if you just read what's written here, the superposition theorem can be used to solve networks with two or more sources. This method operates by treating each source independently. So we'll see how can we actually do that. If you have a circuit with three sources, how can we actually consider the circuit with only one source at a time? So we're going to look at this in more depth in a few minutes. So you can treat each source independently, and the algebraic sum is computed by determining an unknown quantity of the network. Yeah. The superposition theorem states the following. So if it refers to current and voltage, so depending on what you want to find, you can use the superposition theorem to find either current or voltage. So if you find the current, it's a simple question of applying Ohm's law. If you know the voltage, again, Ohm's law to get the current. So either current or voltage would ultimately give you your parameters. So let's read what's written in blue there. Current through or voltage across an element in a linear bilateral network. In a few minutes, we're going to see what the linear means and what the bilateral means. That's what the next slide is going to explain in more details. The current through or voltage across an element in a linear bilateral network is equal to algebraic sum of currents or voltages produced independently by each source, like you see above. So let's look at these two terms now. The theorem mentions two terms which we have to understand. The first one is linear. So a linear circuit is one whose parameters do not change with current or voltage. For example, if you have resistance, inductance, or capacitance, these parameters don't change with current or voltage. If let's say you have a circuit which is producing a current of 1 ampere, your resistance, let's say, is 1 ohm. If you have 2 ampere, the resistance still stays the same. It doesn't change. Same for inductance, same for capacitance. But if you have any parameters, there are some circuit elements whose parameters change with voltage or current. So they are more advanced circuit elements. So what is this linear term is basically saying to you is, if you have any element whose parameters, like say resistance or whose inductance change as the current or voltage changes, you can't apply the superposition theorem. So these parameters should stay the same. Second term mentioned is bilateral. So a bilateral circuit is one whose properties are the same in either direction. We have considered diodes already. I'm going to send you a video later on to complete chapter. So a diode is not a bilateral circuit element, because if you consider the diode on either side, the characteristics are not the same. So if you have any circuit with a diode, you can't apply the superposition theorem because it's not a bilateral. Circuit. Yeah, let me explain that again. If you consider any circuit with let's say a resistor, a capacitor, or an inductor, if you consider the circuit from either side of it, you're going to get the same performance. Okay, so a resistor, if a current is flowing from left to right or right to left, doesn't matter. Same for inductor, capacitor. But if you have a diode, that's not the case. If current is flowing from left to right, it will be forward biased, so you're going to short circuit it. When it's now flowing from left to right, for example, it can be reverse biased, so you're going to open circuit it. It means it's not a bilateral circuit element. So superposition theorem cannot be applied for circuits with diodes or any other element which is not bilateral. I hope you get the point here. So the performance should be the same in either direction. Okay. Now let's start considering now the sources, because superposition theorem deals with sources. So in electrical circuits, we have two main types of sources. One is called a voltage source, and second one is current source. So we are more used to voltage source. Till now, most likely you've been dealing with voltage sources, but there's one type of source called current source. So like the name itself is saying, a voltage source will provide an EMF to you. So it's going to provide a voltage. So a current source is going to provide a current instead of a voltage. So this is how we typically show a voltage source as we know it. So you have a shorter bar for negative terminal, a longer bar for positive terminal. And typically a voltage source will have an internal resistance. So you would want this internal resistance to be as small as possible so that you don't have a lot of drop across it. Because if, let's say, the current flowing here is I, what you would actually measure here at the two terminals, which is being fed to your load, would be E minus the current times R int. Yeah. So you want this internal resistance of your source to be as small as possible so that you get maximum EMF across your load. Yeah. So I guess this one is familiar to you. Now let's look at the current source. So a current source is shown as follows. Now it's shown in a circle with an arrow. So this one, and you have typically at the side of it, you have the current rating. Yeah. And as you can see now, this internal resistance of your current source is not shown across it. Yeah, it's not shown in parallel to it. Sorry, in series with it, it's actually shown in parallel to it. So that's one important difference. We understand why as we go along. Now, what is written in green here is what is the ideal value of R int for current source so that the rated current flows fully through the load. So let's consider what this means. Remember, if I just go one slide back, what did we say about R int here? Means you would want a voltage source to provide, actually if you have E volts being provided by the voltage source, you would ideally want E to be across this. You don't want that internal resistance to create a large drop. Let's say your battery EMF is 10 volts. You would want 10 volts to appear here, but in practice, if you have a very good voltage source, it might be 9 point something, 9.98, 9.99, something like this, because internal resistance will be quite small, so the drop across it will be quite small. So you take that E minus R int, you're going to get a drop here. But what if you are applying 10 volts here, you're getting only 5 volts here. It means 5 volts appearing across your internal resistance of your battery. That's a very bad battery. It means you're having too much drop across it, and this might even mean that some loads don't operate, because when you're sizing a battery for a given application, imagine you have your car battery rated at 12 volts. You expect to get at least 12 volts or around 12 volts, 90.98, 90.9, let's say. But what happens when your battery starts aging, or it starts getting, it starts not being able to provide voltage? That internal drop across its internal resistance start becoming higher and higher. And this causes that your battery doesn't provide 12 volts, it can start providing 10 volts, 9 volts, and this means your maybe your injectors or other elements in your car cannot even operate because it needs 12 volts. Yep, so this is one example. Now, what about the current source now? We've seen the current source, the resistance is placed across the current source. So what can you say about R int here? Should R int be very large or very small? Ideally. So that's what is written here. What is the ideal value of R int for a current source so that the current actually flows free through the load? Remember, you have a load connected across these two terminals here. If I just annotate here, so if I write here small a and small b, so you would expect the load to be connected here. Remember, yeah. If you have any load here, a motor or any resistor, is going to be connected across your current source. So if a current I is flowing here, because this is rated at I, Let's say I is 5 ampere. So this may be a bit unfamiliar to you. We typically use voltage source, like I mentioned earlier. So a current source is also a way to represent a power source. Yep. So if your current source is within at 5 ampere, means the I here is 5 ampere. So what you ideally want here, you want this 5 ampere to flow across your load. Yeah, you want 5 ampere to be flowing across your load, but you of course have part of it which can flow through your internal resistance. This is why we place this internal resistance for a current source in parallel, because you need to share that the main current. For voltage, how you share voltage is by placing the voltage, the resistance in series with the voltage source. Now, how do you actually share current by this internal resistance? Is by placing in parallel, because then the current is split into two. So typically you won't have 5 ampere here. If you get something like 4.9 ampere or 4.95, you're doing a quite good job, because the majority of the current is flowing here. Then you might have 0.05 ampere here. So it means your internal resistance is taking on this small amount. So the question asks you, what's the ideal value of Rin? Rin should be very large or very small, according to you. So if we consider this path here, so the current is flowing across this path, the best resistance would have been that you actually remove this. So this will be infinity. If your internal resistance is very high, so it doesn't take any current, then all this current will be flowing here. Okay, so the ideal value for our current source would be infinity, very large value that it doesn't take any current here. So the majority of current actually flows through your load. So these are two. Let me just clear this. Yep. So these are two different ways you can look at it. If I just go back again, in this case, we said your internal resistance should be as small as possible for the voltage source, so you'll have a drop across it. So E actually appears across the terminal. Now, on the other hand, for a current source, we're saying Rin should be as high as possible, so that it doesn't take any current across this path. It's as if it's an open circuit, so all the current actually flows through your load. So I hope this is clear. Okay. So in applying the superposition theorem, like we said now, we just studied the voltage and current sources. We need to be able to replace each one in turn. Of course, if you have, let's say, 2 voltage source in a circuit, then you're going to replace 1 voltage source, study the other one, and then again replace the other one and study the performance of a second source. If in a circuit now you have 1 current source and 1 voltage source, you will study the circuit with 1 current source, remove the voltage source, then remove a current source and study it with a voltage source, and then add both responses. If I just go back to make sure you understand what we are doing, if we see what we mentioned here in blue there, we mentioned that the superposition theorem allows us to study the performance, the characteristic, if you want, of a circuit with 2 or more sources, be it current source or voltage source, by considering only 1 source at a time. Let's see how it works. We'll study some very simple example, and then in your tutorial sheet, you'll get more advanced example to test, and in your practical also, you have opportunity to consolidate on that. So let's move along. Okay, let's consider one case. Yeah. So since we are mentioning here that we need to replace voltage source and current source, the question is, if you have, let's say, a voltage source as follows, how can you remove that source here? By what are you going to replace it? So in this case here, your voltage source has an EMF of E, let's say, of 10 volts. If you replace it, it should become 0. It means for a voltage source, you have to short circuit this, because it's the voltage across the short circuit is 0. Because let's say you wanted to remove a voltage source, you're going to actually short circuit it. It means you remove it. On the other hand, if you wanted to remove a current source, it means you don't want any current to flow in this part. You're going to open circuit it. I hope it's clear. So for voltage source here, you will short circuit it because you want the EMF to become 0. This is what superposition theorem is saying to you. If you had to remove any source in a circuit, so that you consider only one voltage source at a time, if it happened that you want to remove a voltage source, you will simply short circuit it, because then the drop across this part here in blue is 0. Of course, the drop across the internal resistance will not be 0 if a current is flowing, but the purpose here is to remove that voltage source. Yeah. So if you want to remove voltage source, you short circuit it. So now the drop is 0. It's not contributing anything in the circuit. If you had to remove in a circuit a current source, it means you want to make the current flowing in this part of a circuit 0. You're going to open circuit it, because current cannot flow now. Yep. So just bear that in mind if you want to write it down. I'll just give you a few seconds. If you want, you can draw that. So if you had to remove a voltage source from a circuit, you would short circuit it because the voltage drop across the short circuit is 0. It means you've made the source become 0. On the other hand, if you wanted to remove a current source from a circuit, you would open circuit it because a current across, or the current flowing across an open circuit is 0. Current cannot flow across an open circuit. Okay. Now let's consider an example to show how this is applied. If you get any doubts, do ask, please. I can explain this again. I'm trying to explain a few times to make sure you understand. Let's read this part in this paragraph here, which shows if you wanted to apply the superposition theorem to calculate the current across any part of a circuit, how it works. Let's just read that together. The total current through any portion of a network is equal to algebraic sum of the currents produced independently by source. So we've seen, for example, if you have a circuit with two sources, let's say, irrespective of whether it's a voltage or current source, if you wanted to get now the total current produced across, let's say, flowing through a given resistor in the circuit, then you will have to take the algebraic sum of the currents produced by each source independently. That is, for a two-source network, if the current produced by one source is in one direction, while that produced by the other is in the opposite direction for the same resistor, because at any point in time, you're considering a particular part of the circuit. That's important. So if this is saying if your directional current is different, for one source is flowing, let's say, from left to right, for the other source is flowing from right to left, then the algebraic sum, of course, will be a difference. It's a vector sum if you want. Okay? The resulting current is a difference of the two and has direction of a larger. If the individual currents are the same direction, then you will, of course, add the two currents and they will be the same direction of the currents. So I think this is quite logical what you're saying here. Now, the same holds true for voltage. If you are calculating voltage now instead of current, then it's a question of polarity now. So if you get the polarity the same for both sources, if you get the polarity of potential difference across a resistor to be having the same polarity for both sources, so you simply add it. If they have different polarity, let's say one is plus on top, then minus, or the one is opposite, you will subtract, and it will be, of course, the polarity of a higher voltage. Okay. Now, till now we'll consider superposition theorem for voltage and current. So this one is saying, does it hold for power? What do you mean by that? Let's say in this part of the circuit here, yep, you're calculating P1 as I1 squared R because power is I squared R. So what is I1 here? It's the current that's flowing through the resistor R because of, let's say, a given source 1. I2 now is the current flowing through the same resistor because of a second source. So we're just seeing here this part of the circuit. We're just now considering the load only. So what power you get for voltage source, or let's say source 1 is I1 squared R. The power you get for the second source is I2 squared R. So the question which we're asking here is the power is a sum of these two. The power which you get here. So if you put both sources together, the total current you get is IT, which in this case is going to be I1 plus I2. Yeah, if I just write it down. So from this one, when you have voltage source 1, you get I1. When you get source 2, I'm not saying a voltage source or current source, it is irrespective, it's just source 1 or source 2, you get I2. So based on superposition theorem, IT would be simply equal to I1 plus I2. That's what we take, the algebraic sum of I1 and I2. So that's okay. We've proven that through superposition theorem. Yep. So similarly, if you want to calculate the voltage across R, is going to be I1 times R. The polarity is going to be plus here and minus because voltage always flows from high potential to low potential. If the current is the same direction here, again, you get the plus potential here and a minus. So the voltage drop here is I1R. The voltage drop for source 2 is I2R. Then the overall here, the overall voltage drop across the 2 would be again I1. I just write it down, I1R plus I2R. Yep, so we've seen the superposition theorem holds for voltage and current. So if you wanted to get the overall current here, simply take I1 plus I2. If you want to get the overall voltage drop, you're going to take I1R, which is the drop you get with source 1, I2R, which is the voltage drop you get with source 2. Now, superposition theorem tells us if you have to put both sources together, the voltage drop will simply be the algebraic sum. So is this one here, or for current this one? So this is fine. Now, the question is, can we take now the power of this one, the power we source 1 plus the power we source 2? If we add these two, do we get the total power? So how do we find this out? If you just replace here by IT, we said IT is actually I1 plus I2. So we can replace your IT by I1 plus I2. This is from superposition. You square it and then you times R. So we know from mathematics, this is not equal to I1 squared R. If you expand by mathematics, you're going to get something different. This is not equal to this one. Simply because you have a term which is 2 times I1, I2. If you expand this part here, you're going to get I1 squared R plus I2 squared R. That's fine. But the third term, which is 2 times I1 times I2. This shows us that you can't apply the superposition theorem for power because you have a squaring here. The squaring is a non-linear operation. So superposition theorem holds only for current and for voltage, but you can't add powers. So if you have to find the power across this one, you're going to use current to get IT and then you apply the superposition directly. Don't try to find the individual powers for each source and add. It won't be the total power across. I hope it's clear. Okay. Let's continue. Let's consider some examples now, some examples of superposition theorem. The first one is as follows. If you find this circuit there, so you have a voltage source of 30 volts, you have a current source of 3 ampere, and then our aim is to find what current is actually flowing through R1, a resistor of 6 ohms. So if you apply the superposition theorem, it means we'll consider one source at a time. Yeah. So if you want to consider the current source, let's say, then you have to remove the voltage source. How we do that? We just short circuit it. Okay. If you want to consider the voltage source now, you have to remove a current source. So how we remove a current source? We simply open circuit it. Remember the analysis we did earlier. Now, how you proceed now? Let's say you remove the let's say you want to remove this one. So how we do that? You open this part here. It means no current is being provided in this part, so you have only the voltage source. Now, it's very easy now. If you have 30 volts being applied here, and you want to know what I1 is, not I1 the total current, you get I1 dash now because this is just for the voltage source. So very easy now. What is I1 dash? It's going to be equal to 30 divided by 6, so you get 5 ampere. So you get 5 ampere when you use the voltage source only. Next, what you need to do now, if I just erase, so we can, yeah, I'm just going to erase this part now. So next, what we want to do, so we got I1 dash is 5 ampere. Next, we want to remove this one now. Because this is what we said, you have to remove each source in turn and study the performance. If you remove this one here, how do we do it? We have to short circuit this one. We just mentioned how you remove a voltage source, you short circuit it. So at this point, you don't have the battery, you just have a short circuit here. You have 3 ampere flowing here. So the question is, if 3 ampere is flowing from your current source, because this always provides 3 ampere here, this is the rating of your current source, how much current will actually flow here? So now it's not I1 dash, the current flowing here, let's call it I1 double dash. That's another value, it's not 5 ampere, 5 ampere was the previous one. The question to you is, if you have a circuit now with 3 ampere flowing up here, you have a short circuit here, and you have a 6 ohm resistor here, how much current will actually flow here? Now, it's a very simple question, but many students actually fall into the trick here. If you have this current here, which has to split into 2 paths, it's very logical that if we go along the path with lowest resistance, so the 3 ampere will fully go across this path here. Because there's no resistance here, the 3 ampere will simply go here. It will, no current is going to flow here. Because it's short circuit, there's no resistance to the path of current. It's just like, very simple, if you had to go across 2 paths, one is full of phones, like a resistance is like something preventing current to flow. It's like a path with phones, and this one is a very nice path with sand and grass and so on. So the current is just going to go across this path here. It means this one is equal to 0. Yep. So you don't have any current flowing through the 6 ohm resistor when you connect only the 3 ampere source. So what's the overall current now? I1 is going to be I1 dash with a voltage source plus I1 double dash with a current source. So it's 5 ampere plus 0. So it means overall 5 ampere will flow through the load. Now this is what you're going to find in the subsequent slides. Let me explain that again. So this is what we've just done. So in this particular situation here, we are considering only the current source. So we've short circuited the voltage source. Yeah. So like I've just said, in that case here, if we assume in this case we put I1 dash is the current flowing due to the source, I1 dash will be actually 0. Yeah, because all the current will flow here. Then alternately now, on the second step, you're going to actually take off the current source by open circuiting it. I hope it's clear why we open circuit for a current source and why we short circuit for a voltage source. Now, in this case, what's going to be your I1 double dash? So we've said that the current is going, no current will flow here because it's open here. So the full 30 volts will actually appear across your 6 ohm resistor. So the current I1 double dash will be 5 ampere. 30 divided by 6, you get 5. So what's the overall current? Is going to be I1 dash plus I2 double dash. Sorry, I1 dash plus I1 double dash. The 0 plus 5, you get to 5. Yep, this is what we've just, so this is what we've just explained. So you can see by applying the superposition theorem here, at start the analysis may seem complicated. You have a voltage source, you have a current source. How do you go about? The superposition theorem allows us to consider each source individually, and then we are able to finally get the current which is flowing across a given part of your circuit. Let's consider a second example, again for superposition theorem. So let's consider this circuit here with 2 voltage sources. Yeah, we have 2 voltage sources here, 154 volts and 148 volts. The aim is to find, so whenever you use superposition theorem, of course, you will have an objective. It could be finding the voltage across R1 or the current here or anything. So for this particular question here, we want to find what current I3 is going to flow across your R3 resistor. That's the objective. It could be any other part of a circuit. Okay, so how we proceed? If you want, if I just give a few minutes, you can just take this down in your copy book. So just take down this circuit. I give a few minutes, just quickly draw this. So our aim is to find I3. So as you are drawing this circuit here, I'm just going to explain what we're going to do, steps, and we're going to actually see the steps in the subsequent slides. So we're going to first take off one of our voltage source. Like we said, for example, we can take off the 48 volt source here. So how we take off a voltage source, we just short circuit this one. And then the aim now is to find what current I3 dash is going to flow with only the 54 volts. So now a simple question of having a circuit here with the main current going out and then splitting into 2 paths. So you have 2 paths here, one a 12 ohm resistor and then a 4 ohm resistor. Your aim is to find I3 dash, which is the current flowing only because due to the 54 volts source. So once you've got I3 dash, next step now, you will actually short circuit E1 and consider only E2, the 48 volts. So in this case, your circuit again becomes quite simple. You have a current going out. It's going to actually split into 2 paths here. So split across this path and this path, and then join back and then flow through your 4 ohm resistor. Yep, this is 4 ohm resistor could also be here, doesn't matter. So again, it's a simple question of finding the current which is splitting into 2 and then joining back here. So you could clearly see here, since the current is splitting into 2 paths from this to this, these 2 are in parallel. So you can just replace this one by one common by one resistor and then simply find the total current. Let's see how the steps works out now. I hope you'll be able to draw the circuit. So like I mentioned earlier, you're going to, in this case, it's short circuiting the second battery source, like we said earlier. And then now we consider what I3 dash is going to flow only because of E1. Yep. So if you consider how the current behaves, so the main current actually flows through 24 ohm resistor and then splits into 2 paths at this point. So one path is here and the second path is here. So these 2 resistors are definitely in parallel. You can see they share the same nodes. This one is shared by this part and this part is also shared. So these 2 points are shared by the two resistors, so they are in parallel. Yep. So if you combine the 12 ohm and the 4 ohm, you get 3 ohms here. And then if you take the 3 ohms and put it to replace these two here, then you get a total resistance of 24 plus 3, 27. So the current which is flowing across these two now would be 54 divided by 27, then get 2 ampere. Yeah. Now, this part of the analysis is now doing the other step. So you are removing this source E1, which was 54 volts, and you consider only the 48 volt source. So in this case, we label the current as I3 double dash. So again, if you analyze how the current behaves, so the current starts off here and then goes here, and then you can see this this resistor, and this resistor shares this node. This one has been short-circuited, the source, so you can just forget about this part now. So this one is short-circuit, 0 ohm here. So, and the other node of your resistor is sharing the same node. So these two resistors are in parallel. Yeah. So if you combine these two together, you know the formula for that, product of a sum. So 24 times 12 divided by 24 plus 12, you're going to get 8 ohms. Now this 8 ohm here is simply now in series. Yeah, in series with this one. And then 8 plus 4, you get to 12, and then so you get 4 ampere. Yep. So you should be able to get these answers now. 4 ampere is, if you look at the direction of currents now, you can see I3 double dash is flowing from left to right, whereas if you consider the direction of current I3 dash, it was moving in the opposite direction. Okay. Now, if you take 54 divided by, let me just check something. 54 divided by 20. So you should be able to get these two values and just check something. Yep, so if you work it out, you're going to get these two values here. So 4 ampere is from left, flowing in this direction, as you can see here. It's flowing from left to right. This is the 4 ampere. And the other one is moving from right to left. This is why you subtract it. And so the overall current is 2.5 ampere. Okay, so you can clearly see here, how do we combine these two currents is the algebraic sum. Yeah, in this case here, your 4 ampere is flowing from left to right. So we've taken the 4 ampere, and for the I3 dash, it was the opposite direction. So we subtract. So the overall direction is 2.5 ampere, same direction as your 4 ampere. Yeah, the larger current. So I think you would, I'm going to send the slides to you after our session here. So you would need to work this out on your own, how we actually consider each source individually and how we lump them together to finally get the total current. If you see how the current of I3, the direction shown is from left to right. This is why when you are considering the 4 ampere, you consider 4 ampere to be positive because it's the same direction as shown here. Okay. So this completes your superposition theorem. You will have more opportunity to practice, of course, in the tutorial sheet and in the practicals you will do on Thursday. Now, the next theorem I'm going to consider now, because this is also covered in your practical, is a Thevenin's theorem. Okay, Thevenin's theorem, a very useful theorem. We're going to use that a lot afterwards as well when you consider capacitor charging and other circuit simplification. So Thevenin's theorem is quite different from superposition theorem. Let's look at it. So if we consider Thevenin's theorem, again, we have a term linear and bilateral, which we've already seen earlier. Yeah. So what Thevenin's theorem actually states is that you can replace, yeah, you can replace in any part of a circuit if you have two terminals A and B. We're going to practically see how it works later, of course. If you identify two terminals A and B, can be anywhere in the circuit, across a resistor, across any part, you can always find at that point and across these two terminals A and B, you can always find an equivalent resistance called RTH, TH for Thevenin, and you can also find an equivalent voltage source, ETH. Yeah. So it means if you have a big circuit and you identify a particular two terminals in your circuit, you can always find these two parameters, and then it's very easy to simplify the understanding as the analysis now. So what happens? Let's say you have a load in the circuit across A and B. Let's say you have, I'm just going to draw this for you to make it clear. So let's say you have a load here, CC motor or any load you have in the circuit. Okay. Now your purpose is to know what voltage what voltage and what equivalent resistance appears when you look from the side of the load. If you can simplify a circuit, your circuit will be very complex with a cascaded network with lots of resistors and lots of sources. But if you can bring your circuit to such a simple state where you have your load, you have one voltage source and an equivalent resistance, it's very easy now to work out what's the parameter of your load. If you want to find the voltage drop across RL, simply a voltage divider here, RL over RL plus RTH times ETH. If you wanted to find what current actually flows through your load, again, it's very simple. It's ETH over RTH plus RL, because both of these RTH and RL are in series. Yeah, so this illustrates very well. If you have a very complex circuit, but you have a load in your circuit, and you want to study what current or what voltage appear across your load, you can very well apply your Thevenin's theorem to be able to simplify the circuit and bring it to this type of configuration. You have only one voltage source and one resistance. Let's see how this works. It may seem a bit difficult at this point, but as you go along, it becomes quite simple. Okay, so let's read this statement here. Thevenin's theorem states that any two terminals, so in this case A and B, linear bilateral DC network. Linear, we've said earlier what it means. Your circuit element cannot change its value with voltage or current. And bilateral means it should be the same performance, the same characteristics in both directions, like a diode is not bilateral. We see that earlier. Okay, so Thevenin's theorem states that any two-terminal linear bilateral DC network can be replaced by an equivalent circuit. So this is the equivalent circuit here shown in blue, consisting of a voltage source, which is ETH, and a series resistor as follows, RTH. So this is your Thevenin's theorem. Okay, so Thevenin's theorem allows replacing a circuit as seen by designated load. So this is typically where your load will be across A and B, but you can't see the load at this point because we've taken it out, but we can easily put it back. This is how the Thevenin's theorem works. If you wanted to study the equivalent circuit at a given terminal, you have to take out this the component you have across A and B, and then you put it back later. We'll see how it works. Okay. So Thevenin's theorem allows replacing a circuit as seen by designated load by an equivalent circuit consisting of only one voltage source called ETH and a series resistance RTH. This can be used to simplify circuit analysis, especially if the load resistance changes. I will explain what that means. What is load resistance change? Okay. Yeah. So let's consider this example here. So let's say you have a circuit like this with one voltage source here. You have R1, R2, R3. But this is where your load is, RL there. So what Thevenin's theorem allows you to do is, it allows you, if I just annotate again, so it allows you to simplify. So this is your load here, but two terminals across your load are A and B. Yeah, so you can find again your A and B's here. Okay, and what have you been able to do now? You are able to simplify all this part here, which can be quite complicated, to a simple voltage source ETH and only one resistance RTH. And then of course you put back your load RL. This becomes very simple now. So if you had a circuit where RL is changing, it doesn't become difficult to analyze now, because this is what is the voltage across RL is very simple. It's always RL over RL. Sorry, let me write that again. So if you want to find the voltage source here, as the voltage drop across your load is RL over RL plus RTH times ETH. That becomes very simple as follows. So if this one is changing, this one is changing, doesn't matter. Sorry, this one is changing and this one is changing. It's not a problem now. You can very easily analyze the circuit. But in this case, if you consider this and this circuit here, it becomes quite difficult to analyze the circuit performance when your RL changes, because every time you have to go back to your circuit and analyze it over and over again here. But here it's quite simple to analyze. Yeah. So this is one way your Thevenin's theorem allows you to simplify circuit analysis when your load is changing resistance. But even if your RL was not changing, you can clearly see here if your RL, if you want to find the voltage drop or the current flowing, it's pretty simple. This one is much more simple than this one. Okay, now let's see how the Thevenin's theorem works. So the steps may seem to be a lot here, but not at all. It's quite simple. The 5 steps you're going to look at in a few minutes are quite simple. So when you are considering Thevenin's theorem for a circuit, you always need to see what portion of a circuit do you want to apply the Thevenin equivalent circuit to. Like in this case, it was clear it's A and B because this is where your load is. So whenever you want to apply Thevenin's theorem to an electrical circuit, you will have to know at what two terminals do you want to actually apply it. This is fundamental. So first, you will need to find that and then remove a portion of the network. Like here, if you want to analyze across NB, you will have to take out your RL. RL would not appear in the analysis to get RTH and ETH. This is very important. You have to clearly remember this. Yeah. Whenever you're applying Thevenin's theorem, if you've identified A and B to be your two terminals, then you would take out RL. It would not be in the analysis until the end when you put back ETH and RTH, then you would put RL back. This is what it's saying. Remove a portion of a network across which a Thevenin equivalent circuit is to be found, and then you mark the two terminals A and B like here. So you take this out and then you mark it A and B. At this point, it means your circuit is as follows. It means you don't have this one here. You simply have the part in blue now. This is where we're going to analyze the circuit to be able to get your ETH and your RTH. And then once you find these two, then at this point that you place back your RL. Yep. Okay. Now we've done step 1 and 2. Let's see how we get RTH now, which is the third step. So once you've removed a portion of a network across which you want to find the Thevenin equivalent circuit, and you have marked your two terminals, then you have to calculate RTH, which is a Thevenin equivalent resistance. Let's see how it works. Calculate RTH by first setting all sources to 0. We know how to set all sources to 0. We have already learned that before. The voltage sources are short-circuited and current sources are open-circuited. We've seen that already. So to find RTH, you have to just get resistances, be they short circuit or an open circuit or any resistance in ohm. You can't have voltage or current sources there because you can't work with a resistance of voltage source or current source. You have to remove everything. So how you remove voltage source? Short circuit. How you remove current source? Open circuit. And then finding the resultant resistance between the two terminals. Okay. Yeah. So let's see how this is done. So in this case, if you go back, let's say you have, I'm just annotate again. So if you have taken this one out, yeah, then it's saying now you have to take out all your sources. So you will short circuit this one because you short circuit voltage sources. Now, what are we saying here? If you look on this side, what resistance do you see? This is what we're saying. Remember, RL is not there. How we typically do that? Imagine you send a current here, it has to come back here. So what part of the current takes? It flows here. Yeah, it splits into two, and then it flows. At this point, it wants to flow here, but this one is already short circuited, so no current is going to flow across this one. This RL is as if there's nothing here. So this current is going to flow here, split into two paths, then go straight across this one, and then come back. So this one here is as if it's not there, because it's short circuited. It's in parallel with a short circuit. So this current is going to flow. One part is here, one part is there. So it flows here. And then this current jumps back and comes here. Means your RTH is simply will be R2 in parallel with R3. This is going to be your RTH. So how you calculate RTH? I use this technique. You send a current and see how the current behaves. Let me explain this again. So you set a current here at capital I. It splits the two paths here. We call this one I1, I2. Now, since this I2, when it comes at this point here, it needs to split two paths. So typically, it has to split into two paths. But like you've seen earlier, it's a short circuit. So a current will just flow through the short circuit. It's not going to, any current will not flow through R1. It's just going to take the path with no resistance. It means R1 is short circuited. It has no resistance. It's not contributing anything to the circuit. So this current I2 simply flows here, and then comes back. So what comes here is I2, and it joins back. It means overall, what resistance to be seen here, which is called RTH, is simply R2 in parallel with R3. Yeah. So if you calculate this, you get your RTH. Next step, to find, yeah, we've not seen that. Let me just continue with the step. So this is how you find RTH. Again, we'll see that through examples in a few minutes. So we've seen step 1 to 3 till now. The fourth step is to find ETH. ETH is found by, of course, returning all your sources, because you get a voltage drop across the terminals A and B because of the voltage source. So next step, you replace all your sources and you have to find what voltage will you measure across A and B. Yep, so if I go back again to this circuit here. Okay, so at this point, we're going to put back our E. Yeah, and then we want to calculate, this has been removed right from the start, it's not there. We want to see what voltage do we measure across these open terminals, because RL is not there. What voltage will you measure across these two terminals when you have an E there? So what is the voltage across A and B? Is simply the voltage across all three. You can see they are sharing the same nodes. There's no RL here. Remember, we remove RL right from the first step. So RL is not there. We want to find what voltage will you measure across A and B when you put back all sources. In this case, we have only one voltage source, so we put it back. So this voltage which you measure here is called ETH. This is called the Thevenin equivalent voltage. So how we work this out? Very simple. So imagine you start a current here. Yeah, you start a current here. It splits to two paths. Yeah, and then so these two resistors actually in series, because same current is flowing in. No current can flow here. Just don't be confused by that. Some students are confused by that. There can be no current flowing here because it's an open circuit. So the same current, if this is capital I, yep, this is now I1 and I2. Okay, it splits to two paths. Now once I2 flows here, the same current I2 flows for R2, R3 as well. So this is also I2. And then it goes back, joins to I1, and then you have your overall I, which is here. So if you had values for R1, R2, R3, it's straightforward. So these two are actually in series. You can just lump them together. It becomes a simple voltage divider. So you can very easily find your drop across the resistors. Okay? So if you put values there, it's not a problem to work it out. Yep, but we'll see in a few minutes some examples. So once you find that ETH now, which is the voltage you would measure across your terminals A and B without the load I've said, but with the voltage sources replaced back, then you get to ETH. The final fifth step is simply now to draw your Thevenin equivalent circuit, which would be this one now. So this is at this point that you put back your RL, then you put your ETH, and then you put your RTH, and then you have your Thevenin equivalent circuit. You simplify now your circuit analysis considerably. You have only one voltage source and one series resistance with your load. Now it's very, very straightforward to do any analysis you want. And you can cross-check that based on the examples we do. If you analyze the performance of the circuit, let's say voltage across AB, with the whole source, with the circuit, original circuit, you will get the same answer, of course, with the Thevenin equivalent circuit. That's the whole purpose. Okay, so let's consider some example now. So let's say this question: find the Thevenin equivalent circuit for the network in the shaded area of the circuit below. So I give you a few minutes, just draw this circuit quickly, and then we'll do it together. Yeah, just quickly draw what's in your comic book, and then we'll see how we apply the Thevenin theorem here to find a Thevenin equivalent circuit. So as we said, step number one was to identify which portion of the network you want to find a Thevenin equivalent circuit. Here it's quite clear. It's already labeled A and B to you, and this is your load. So it means first step you're going to do now is you're going to take out this one, so you can draw a new circuit now without RL. So just remove RL because this is the first step, and then you're going to label A and B. Okay. So this is your first step, is to take out this part. So RL would not be in the analysis for RTH or ETH. That's very important. If you do this step wrongly, you can get the wrong values. Okay. So I hope you've been able to draw a circuit. Now let's continue. It's the steps in the first slide. Now this is the first step now. So in this case here, we've done step one to take this off and label the terminals A and B. First step is to find the RTH. To find the Thevenin equivalent resistance, like we said, you have to remove all sources. In this case, we had one voltage source here, so we have to short circuit it. And now next we find what resistance would you measure if you look from this side? This is typically how it's shown. If you look from this side, I can draw an eye here if you want. If you look from this side, yeah, if you look from this side with your eye, what resistance would you measure here? The technique I use is I send a current here. Yeah, if you send a current I, and then you see how this current behaves, the current is going to split into one path here and a second path. So these two are actually in parallel. And of course, these two current I1, I2 would merge back to get to capital I here, has to be the same current returning back. So it means RTH is simply 3 ohm in parallel with 6 ohm. So RTH is equal to 3 in parallel with 6. You can see the current splits into 2, and these two are actually sharing the same points here. So this point is shared by this one, and this point here is shared by this part here and this part. So the two resistors are in parallel. So if you can take product over sum, so you get 18 over 2, you get 2 ohms. So your RTH will be 2 ohms. That's the first step which we've said. Yep, I hope it's clear. Very simple example here, just to illustrate the application. So if you get RTH is equal to 2 ohms, if you don't get it, you just let me know. I can explain again. Okay. Now, once we've done step 1, 2, 3, so first step is to get RTH. First step is to get RTH. So to get RTH, we put back our voltage source, and we want now to measure what drop would we get across A and B without the load, of course. Yeah. So we've got our 2 ohms. Now this is the fourth step where you find ETH. So you put back your voltage source, like we said. Now the aim is to find what is ETH here. So ETH is nothing but the potential difference across a 6 ohm resistor. So if you apply voltage divider rule, so 6 over 3 plus 6 times 9, so you get 6 over 9, so you get 6 volts. So ETH is going to be your 6 volts. So it's a very simple voltage divider here, because your ETH is nothing but the voltage drop across a 6 ohm resistor, and it's a voltage divider. If you want, you can also see how the current behaves. So current goes here. No current can flow here because it's an open circuit. Remember, there's no resistor here. So the current can only flow across the 3 ohm and the 6 ohms. So the total resistance is these two are in series because same current is flowing across them. It's 9 ohms. The current now is 9 divided by 9, you get 1 ampere. So the voltage drop across the 6 ohm is 6 times 1, you get 6 volts. So you can use the voltage divider rule, or you could find total current and then just use ohms. Yeah. So this is the fourth step. Final step, this is critical what is shown here. Remember, we've got ETH 6 volts. So this is your ETH. We've got RTH 2 ohms, that's fine. And this is where you put back your RL. So RL did not appear in any of analysis we've done from steps 1 to 4, which is fundamental. So RL doesn't appear in analysis. At the end completely, now you put back your RL. And once you do that, now if you wanted to analyze the circuit, how the voltage over current flows in the circuit when RL is varied or for given value of RL is very simple. If, for example, your RL is 2 ohms, very simple, the current is simply 6 over 4, and the voltage drop across the load is simply 2 over 4 times 6 is simply 3 volts. And see how the circuit analysis becomes very simple once you've got your Thevenin equivalent circuit. Yep, so this is what you've done. Yeah, so I've shown some values of for RL and what do you get. So once you've got your equivalent circuit like this, it's very easy now to just plug different values of RL and find the voltage or the current. That's straightforward. Okay. Let's consider a second example for Thevenin theorem. Yep. So this one has one current source. Yep, one current source here. And your aim is to find, again, you have to identify your term. I'm just going to go quite quickly here because we've done it once. So let's say your aim is to find the equivalent Thevenin circuit across the 7 ohm resistor. So you will take this one out first step. Yep, and then you label your terminals. Now, first step, you're going to find the Thevenin equivalent resistance. In this case, this one is a current source, as you can see. So this is going to be open circuited. If I just show it to you. So this is going to be, you take this one out when you find your RTH. So this one is an open circuit because current sources are open circuited. Okay. Now, if let's say this one is taken out right from the start, now you send a current here. The current simply flows here. and flows here and comes back. No current can flow here. So this case is very simple. Your RTH is these two resistances are in series now because the same current flows here and comes back. So the same current flows through these two resistors. Your RTH is simply equals to 6 ohms. Next step, you put back your voltage source. So if I just erase this, so you put back your current source, and then you want to find what drop do you get. If I just draw this, yep. So you want to find what voltage will you measure across this one with 12 ampere. So if 12 amperes flowing here, how it behaves. So this again maybe quite confusing to you. So this one is actually not here. This part is not there. So terminals A and B are just two terminals. So what the 12 ampere would actually do? The 12 ampere would simply flow through the 4 ohms. No current can flow here because if you imagine you have a current flowing here, where will it go? Because it's open. So the whole 12 ampere has to flow through the 4 ohm resistor. It means what you measure across A and B is simply the drop here. This one has no current flowing through it. It's going to contribute nothing as if this is not there. Okay. So what is going to be ETH is simply going to be 4 times 12, you get 48. You have to understand these fundamentals very well. So ETH will be 48 volts. Again, no current can flow in this path because where will this current go? Because A and B are open circuit. Yep. So you get to ETH and your RTH, and then you just put it back. Now all the steps are summarized. Yeah. Just clear all the drawings. Yeah. So all these steps are summarized here. So we've just found our RTH to be 6 ohms. Yep, we got 6 ohms because it's 2 in series. And your ETH, as we've said, no current has to flow here. So all the current is flowing across the 4 ohm resistors. So your ETH will be 48 volts. Yep. And this is your Thevenin equivalent circuit with 48 volts here and 6 ohms. And now at this point, if you wanted to find the voltage across your R3 7 ohms, is simply 7 over 13 times 48. If you wanted to find what current is flowing through R3, it's simply 48 divided by 6 plus 7 because they're in series. Okay, so Norton's theorem, we will continue in another video. Yep, I'm going to do that. So for those doing practicals on Thursday, so we've covered the superposition theorem and the Thevenin theorem. This should put you in good state for the practicals. And of course, you have a tutorial sheet on this very important chapter because we're going to use it subsequently. Okay,